Okay, so I'm back. I'm actually on page 227 in the notes, but it involves some figures that I'm not super good at drawing, but I'm pretty good at making GeoGebra create those. So what we're going to do is we're going to take a look at that. So I'm on my website and I'm scrolling down to the notes that we're on, note 17. Here's a link to some GeoGebra sketches. I'm going to click that. I recommend you take a look at this one, Path in 2 and 3 dimensions. It's pretty cool. Animate the slider, you'll see. What we actually want though is direction cosines. So I'm going to click that, and it's going to open up eventually. Okay, so what we have in this picture is we have a vector. So I don't know what this is spinning around. It's like not spinning around the origin. Let me hit the home thing. So when you hit the house down there, like as soon as you move it, the house shows up. It like takes it back to the original orientation, which sometimes you get lost like literally in space. And hitting that will like at least bring you back to some place you can be sure about. So this is our vector. It's in the first octant. It doesn't matter where it is, but like most of them actually are in the first octant. So like not most vectors. Every single picture that you see of this concept is what I mean, will be in the first octant. So what I'm going to do is I want to find, there are three things. There are three angles that this vector makes with the positive coordinate axes. So there's a positive x, positive y, and a positive z axis. This vector makes an angle with each of them. Sometimes, though, that angle is not exactly where people expect it to be. So if you are on this page, hopefully, you see there's like a lot of things here. And all that we really need to do is we need to click on things. So what I'm going to do is I'm going to create a polygon that we can look at that will help us find what's called alpha. So the angles are called alpha, beta, and gamma. But we actually find their cosines for some reason. The reason being that the cosines are enough to distinguish them, and there's a cool thing that has to do with the direction cosines. So what we're going to do is figure out what is alpha. So alpha is the angle between the vector and the positive x-axis. So the positive is the red one. So the angle between them, which should be like here. So I'm going to turn on that polygon and then rotate it a little bit. And you can see the polygon is like on a diagonal of the rectangular prism that you might draw. And then alpha is the angle between the vector and the positive x-axis. So if I click on this, there you go. That's alpha. And what we're going to do is we're going to find alpha using cosine. The reason we'll use cosine is, look at what we have here, right? So I've oriented it. This is the x-axis. So I actually know the side adjacent to alpha, and then this is the vector. So if I find the magnitude of that vector, I would know the hypotenuse. So I can find the cosine of alpha by doing whatever the x coordinate is of the component form divided by the magnitude of the vector. And that's going to be really useful. So that's our alpha. So let me turn these off. Beta is the angle between the vector and the y-axis. So that's going to be, okay, so there's our polygon. And then if we put in the angle beta and then turn it until it kind of feels like a triangle I want to deal with. So I'm gonna do this. So the green axis is the y-axis. So the side adjacent to beta is just the y-coordinate of the component form. The hypotenuse is still the vector. So I can find the cosine of beta by doing whatever the y-coordinate is divided by the magnitude of the vector. So that's how we're going to find the cosine of beta. And then in my experience, for whatever reason, well, not for whatever reason, because it's actually the most obvious. Not most obvious, but it's the easiest to picture. None of them are really obvious. Gamma, which kind of looks like a diving fish, it's like a Greek letter, is going to be the angle between the vector and the positive z-axis. So it's the easiest one, I think, to picture because it's kind of like I feel like everyone when they're a little kid at some point has, I don't know why you have this, but you have like a triangle taped onto a pencil. I don't know why you would have that, but if you take it and you like roll it in your hands, it makes like a cone and you can kind of like see it. Gamma is the angle between the vector and the positive z-axis. So here is gamma. So if you look at this, if you remember the way that you can orient this, I can only tilt this forward and backward. I can't actually tilt it sideways, so I'm not going to be able to reorient it so that it looks like the way I like to draw my triangles. But if this is my angle, the side adjacent to that angle is definitely the z component, the z component of our vector in component form, right? So the z component is adjacent. The magnitude of the vector is still the hypotenuse. So I'm just going to do cosine of gamma is whatever z is divided by the magnitude of the vector. Okay, so that's kind of the visual. And now what I'm going to do is switch back over to the notes. And this might take me a second. And let's fill in some notes about this. Okay, so alpha is the angle between the x-axis and the vector, right? So in this picture, so maybe now you can better appreciate why I decided to use GeoGebra for this. In this picture, it's really hard to show, but like this angle would kind of be alpha. And so like you can reduce it. You can take a triangle out of there. It's like this, right? Where this, in this case, so I should say, we're doing this specifically for the vector 3, 4, 5 right now. You could do it for any vector. It doesn't really make a difference. But this is 3. Oh, let me do that thing where I highlight instead. I feel like that worked well for me. All right, let's see. So this part right here is going to be 3, right? And that's going to be there. And then this part, let's do good grief. This part, that's not a highlighter. This part, right there, that's actually the vector, right? So that is going to be right here. And so I actually need the magnitude of the vector. So I'm going to, well, right now I'll say the magnitude of V. And then let me calculate the magnitude of this vector. So how do we calculate the magnitude of a vector? We do, stop. Okay, the magnitude of the vector is going to be the square root of 3 squared plus 4 squared, which is 5 squared, and then plus 5 squared. So this is radical 50, so I'm going to say 5 root 2. And then our angle that we're looking for is called alpha. And so I know that the cosine of alpha is 3 over 5 root 2. I'm not going to rationalize that because it doesn't look any better if I rationalize it. Well, I mean, maybe it looks better, but it doesn't do anything for us. So let's find beta, or really we're going to find the cosine of beta. So it's unusual to actually find the angles. You more often than not find cosines of the angles, which like, I don't know if that like ever really makes sense to people initially. But our triangle in this case will be here. Let me draw a triangle. Okay, it's a right triangle. Let me go back. I don't know. Some people freak out if you don't put in your right angles. So this, because it's 3, 4, 5, this will be, what color was that? This will be 4. And then our vector is here, which will be here in our triangle. Thinking in plane slices is so useful. When I'm doing things in 3 dimension, I pretty much always try to picture like, what does this look like if I just like slice it and just look in a plane? So that's what I'm essentially doing here. I'm just looking at like the parts that I need. And so that would be, I think this, I don't know why I highlighted that, but anyway, that's going to be the magnitude of V again. And so the cosine of beta, I feel like anyone who really cares about how colors work out would probably be screaming about these because I am not putting any thought into this. So the cosine of beta is going to be 4 over 5 root 2 because it's same vector, so same magnitude. And then I'm going to do the same thing for gamma. Gamma in all ways is pretty much the easiest one to deal with. So we get this, and then we're going to get this. And I'm doing a great job. This is gamma. All right, here we go. Let me draw a triangle. So I'll draw the triangle the way that it's like currently oriented, even though I hate this. I like my triangles to always have the angle we're interested in. I should fill in beta here. Are these good notes that I'm taking right now? I don't really know. I mean, I'm doing my best. And, well, at least I'm giving it my all. I don't know if I'm necessarily doing my best. So this will be gamma, which kind of looks like that. I'm not necessarily an expert on drawing those. This segment right here, highlighter, come on. This segment right here is Z. So that's going to be 3, 4, it's 5, right? Because we're given the vector. And then this is our vector. So this is going to have a magnitude of the magnitude of V. And so we can find cosine of this. So this is one of those videos where, man, if you're into watching videos at like 1.5 speed or whatever, like this is a good one to do that for. So cosine of gamma is going to be adjacent over hypotenuse, which is the magnitude of the vector, so 5 root 2. You could simplify that, but there's really no need to. So in general, when we get the cosine, the direction cosines, it's not like a super hard concept other than picturing them. Picturing them is super hard, like until it's just like embedded in your brain. It's hard to like think of planes that are at angles to each other. I mean, like look at the room that you're currently in, and now like try to imagine the plane that goes from like the top of the ceiling to the right of you to the like bottom of the floor to the left. Like picture that plane. It's not easy to do. Bottom of the floor, whatever, where the floor and the wall meet each other. Top of the ceiling. That sounds like a weird thing you might say to each other to like greet each other. Top of the ceiling to you. Okay, so cosine of alpha is just going to be a over the magnitude of v. Cosine of beta is going to be b over the magnitude of v. And then cosine of gamma. So some of you might be getting a little excited if you're thinking about vectors here, because something is kind of happening, right? So we took a over the magnitude of v, b over the magnitude of v, c over the magnitude of v. It's like we took a vector and divided it by its magnitude, and then took each of the components. So you get this really interesting thing because you get cosine of alpha, cosine of beta, cosine of gamma should be equal to, it's a over the magnitude of v, it's b over the magnitude of v, and it's c over the magnitude of v. Ugh. Okay, I got lost there, writing a lot of things. But this is just 1 over the magnitude of v times v, which is the unit vector of v. How exciting is that? Like, it turns out that there's this like cool link between unit vectors and direction cosines. I think that's amazing. Another thing that I sometimes like to think about is a unit sphere, like where you have a sphere in space, and like are there famous angles for the unit sphere? I don't know. Like maybe you should check that out. Like, I don't know, Google search perhaps. All right, I'm going to stop this here. I will be back in another video to do more stuff. So I hope you are finding this kind of helpful.